Swayam Prabha. Digital India. Educated India.
So, in the last part of the discussions on the interfaces, I just like to take what is the effect of these interfaces on the stability of the system. Okay, and I will take two examples on that, which I have taken from another book and show you how things can be done. Okay, let us suppose the first example, let us suppose I have a system, okay, which is alpha phase, and within this big alpha phase there is a small grain, okay, small grain, and this is alpha alpha, remember, because this is same grain, and let us suppose the number of moles of the alpha in this grain is basically n prime, and in this case is n double prime. Okay. Let us suppose that this is a bigger matrix or bigger grain and which is a small grain. So, we can write down the total energy of the system, the free energy of the system, okay, is like that. Obviously, is molar energy because these two are the same phase, so therefore, G will be same. So, I can write down this is as a G molar energy. Normally molar energy system is written based like this because there will be a boundary here. So, this is nothing but sigma Ai gamma I, that you see this is the bulk energy, bulk free energy system, which is small n. This is for the interfaces, all the interfaces summation together, plus it will have strain energy effects, and strain energy effect will be n V delta Gs. What is this? This is again n is the number of moles, B is the molar volume, and Gs is the strain energy. Okay, this I have already given you some formula for sigma and for mu square. It can be actually simple for mu square delta and something else, right? What was that? Some other parameter I wrote. Something else was there. Anyway, this is nothing but a strain energy. Okay, because this is your shear modulus and this is the missplit. This can be calculated by many means. The fact that there is a strain in this at the boundary between these and these because of the missplits, you will have a extra energy terms. So, let me just write down these same things for both and this is per volume, remember this is strain energy per volume. On the other hand, surface energy is per unit area, and this is also per unit volume because this is the bulk energy. Now, I can write down because of the small grain, this is small grain inside, this is small grain inside. So, therefore, I can write down Gs of the small grain is basically equal to n prime G, n prime is the number of moles, plus summation of Ai sigma I. Remember, the reason I am writing Ai sigma I is because I do not know whether all the interfaces of this small grain along all direction is same isotropic or not, may not be. Then we need to add up because gamma will be varying depending on the crystallographic directions, and plus obviously it will be n double small grain inside a big grain, inside a big grain. So, that is for the small grain, that is for the interface, and that is for the G, okay, G of the big grain, plus there will be strain energy. So, n strain energy will be depending on this one V and delta Gs. So, for the sake of simplicity, let us assume the strain energy is very small, okay. This is not there at all. then it will be much easy to calculate, then we will later on include that part. So, I can actually then take total differential like this. Obviously, this will be G d n prime plus sigma gamma I, okay. Gamma does not depend on this n. So, then this is dAI dNi, sorry, dn prime, not I, plus n double G dn double prime by dl prime. Okay, we have assumed initially that this part is not existing. Now, what we can do? Let us suppose we have a transformation happening in which some dn prime moles are getting transferred from this small grain to the big grain. What will happen then? If dn small prime of these atoms are getting transferred from small grain to this grain, and obviously then we can write down that minus dn prime, obviously dn prime is lost by this grain, this will be gained by the big grain, it will be mass cannot be destroyed. So, therefore, any loss from this will be gained by that, and let us suppose these are all equal, because gain loss is equal to gain. So, in that case we can write down dgs because of this is equal to minus dgdn plus sigma I, basically we replace everything by dn, that is what we do, plus g, something, some mistake I have done, yes, dn, here also dn, right. Okay, so dn, now this dn will get cancelled, obviously loss of free energy by this, because this is same phase, it will be gain of that. So, you can clearly see dgs is nothing but sigma gamma I dAI dn. Okay. Now, if we assume, if we consider as a spherical kind of a grain, okay, let me do it here. If I assume a spherical kind of a grain, as for a spherical grain, we can write down dA by dN by say dV by dA, sorry, dA by dV multiplied by dV by dN. Now, for a sphere, we know area is equal to 4 pi square and volume is equal to 4/3 pi r cube, and if we do the mathematics properly, this will be coming like a 2 by r into V, V is the volume. Okay. So, therefore, if I do it, this is nothing but dgs becomes sigma, okay. So, sigma will be gamma I, and this one which you have done recently, that is what is here, twice r by V. So, if gamma is, it says only one interface, and sorry, this will be minus again. Why? Because somehow we have done some mistake. Yes, that is what is the case here. So, because this is a loss, and that is what I was thinking. So, okay. So, then finally, if I consider dg for a single interface, dgs by dgn, it will be minus gamma twice V by R. Okay. So, that is what you see, this is a Vm, Vm is the molar volume. So, what you clearly see here, that whatever is the value of gamma Vm R does not matter, okay, where basically R is the radius of this small grain. The change of free energy with respect to change of n is always negative. So, that means what? This simple calculation tells you that this small grain will vanish very soon, because transport of the atoms from the small grain to big grain is leads to reduction of the free energy or negative value of delta G, and this negative value of delta G will make the small grain dissolve completely, or rather the small grain will be consumed by the big grain and it will be part of the big, this mass will be part of the big grain. And therefore, without considering the strain energy, this is what is going to happen. Now, if I consider strain energy, which is obviously positive, suppose if I consider strain energy here, okay, let us do that now, simply by addition of terms, okay, what will happen? That is what I will show you in a simple calculation. So, this is nothing but V delta G S, okay. And so, therefore, I can write down this is V delta G S d n prime by, okay, d n prime, yes, because this is n prime, and again this will be V delta G S d n prime. So, clearly you can see there will be extra term here which is V delta G S, okay, and this is V m. Now, because of the strain energy effect, I cannot simply say whether the change of free energy will be always negative. It cannot be, may not be actually. Depending on the value of Gs, the strain energy, depending on the value of the strain energy here in this term, this value, these things, because of that, the delta Gs might go to negative or might go to positive. If it goes to positive, this transport of atoms from small grain to big grain is not allowed anymore. So, therefore, interface has a strong role to play depending on the type of interfaces, whether it is coherent, semi-coherent. If it is a coherent interface, the delta Gs is very small. If it is a semi-coherent interface, still it is small, but not as small as is coherent. But if it is a completely incoherent interface, delta Gs is very, very high. As a Gs, delta is very, very high. Because of very high of delta Gs, this negative term can be completely swamped or taken over by the positive value of the Pm delta Gs. And in that case, this grain will remain inside this large alpha grain and you cannot remove it. So, that is the actual effect of strain energy on the whole phase transformation. So, in actual reality, real case, we have to consider both the effect of these interfaces because of the surface energy of the interface plus the strain which is generated because of incoherency or semi-coherency or coherency, whatever is the situation, all will lead to some kind of strain, but value of the strain will be varying depending on the type of interface you create. So, this is exactly I wanted to tell you that by simple thermodynamic analysis, even free energy analysis, one can probe that this is possible to actually create have different kinds of situations mathematically or theoretically possible. One can actually do as in simple other analysis. Let me just give you as a part of your home assignments. Let us suppose I have instead of this I have a matrix and I have a precipitate beta, okay, and therefore I am asking the questions, what will be the conditions of free energy versus the number of moles transferred from here to there when I transfer dn number of moles. What will be the free energy functional or as a function of both surface energy and the strain for such a things to happen in the thermodynamically possible way. So, you can actually do as a part of home assignments. Remember here both the phases are different. So, therefore, we cannot consider G to be same for both the phases. The bulk free energy will not be same and there, here. So, G of alpha and G of beta or G of beta and G of alpha one needs to consider, and one needs to consider interfacial energies between beta and alpha plus the strain energy of beta and alpha, and finally get an equation. It will be much complicated than what I have derived, but you can try. Okay, so in the last 5-6 minutes I have in this lecture, let me just introduce the new concept which we are going to deal with, and that new concept is basically nucleation. See, we have thermodynamically dealt with the systems, their surface energies and their strain energies, but the phase formation or generation of a new phase is also depends on whether we can nucleate it or not in the system, and that is why the nucleation becomes important. If you consider solidification, so let us suppose if I am solidifying a solid from a liquid, simply what are the different stages of solidification? First thing what will happen is basically in a very schematic way is that you will have small clusters of atoms come together, that is what is shown here, small cluster of atoms which is shown as a large number of sides. This is the one, this is another one. 4 atoms cluster or maybe 8 atom cluster or maybe 16 atom clusters will come together and form a embryo. Embryo is the small the first stage of formation of nucleus, and then these small pieces, 4 atom things, they are getting added. You can see here 1 2 3 4 added, then some more added, and when the size will become a critical one, then only the nucleus will form. So, that is the first stage of liquid to solid transformation. In fact, this is the first stage for solid to solid transformation also. Furthermore, what will happen? Furthermore, these atomic clusters will join in a systematic way to each of these nuclei. There are 1 2 3 4 5 nuclei. So, therefore, or maybe more, and each of these clusters of atoms will keep on joining with the nucleus, and then they will become bigger, but they will be becoming growing independent of each other, but they do not know whether the other things are existing in the liquid or not. So, therefore, when they will be becoming bigger, that is what they are seeing, these blobs are becoming bigger by joining more and more clusters, and finally, when they will meet, they will form a boundary. That is what we have been discussing for the last few lectures. This is a grain boundary then. So, that means in a real solidification there will be nucleation, growth, and finally formation of grains. That is what actually happens. So, any phase transformation, these are the two stages what happens. One, the nucleation of a new phase, second one is the growth, and we have to deal with separately. As growth will be part of all the phase transformations, so we will be discussing in each separate cases, whether it is a liquid to solid transformation or solid to solid transformations, whether single phase or multi-phase, we will discuss separately for each of these different phase transformations, but nucleation is something which is generic for all of them. That is why nucleation has to be dealt with completely separately, and we will analyze all the theories and tell you how we can apply the nucleation theories to determine the nucleation rate or the other factors which comes into picture. And as you know, nucleation is nothing but a formation of a tiny stable solid particles or solid phase, not particle actually, from the liquid or a solid. It can be like maximum 100 of atoms, depends on the type of systems. Normally it is 50 to 60 atoms or 1 to 2 nanometer diameter. And in order to form a nucleus, you must have to have an undercooling, because you are creating a new interface. How? Just to give an idea that bulk in this case of the atoms on the liquid. So, they have random nature, they will be moving in the liquid randomly. Only few of them came and join and form a cluster. So, therefore, only few of them actually are well ordered, crystalline order is present in few of these atoms. So, thus the interface between these well ordered atomic clusters and the liquid is diffuse. So, because of that, that means the atomic arrangements in the liquid atom in these well ordered solids are distinctly different. Because of that, there is this definite interface created between these clusters and the liquid, and because of the atomic arrangements are different between these well ordered crystals and the liquid, there will be energy associated with the interfaces, and this energy is positive, just like surface energy. I have just now given you the mathematical examples of how the grain grows inside a small grain goes inside a big grain. Similarly, here it is basically small crystal forming inside a big liquid. So, same situation, the surface energy will come into picture, and this surface energy is a positive in nature. Therefore, that energy must be supplied by the system, and this supply of energy is only possible when we undercool the liquid, because free energy systems has to be there, positively available to the system to take care of that. That is why undercooling is very much required. Now, the larger the extent of intercooling, greater will be number of nuclei form that we will see in the detailed calculations. Now, nucleation, which is very generic in all kinds of phase transformations, are mostly heterogeneous. That means nuclei forms on a solid surface, it can in a solidification it can form on the walls of the mold, or in a particulate on liquid, or in a solid case it can form on an interface like grain boundary or a dislocation or a twin or even any other interfaces inside a solid. So, this is the most prevalent one which is observed in the real situation. The one which is easy to deal with, but rarely observed in the literature or in the experiments is homogeneous nucleation. That means nucleation can form everywhere in the system. There is no preferential site for the nucleation. It may not be that it has to form on a boundary or it has to form on a some kind of a solid particle or not. So, the ice starts formation in an ice tray when it happens, that is the case of heterogeneous nucleation. Those of you who have seen how the ice solidifies in an ice tray probably have seen that the ice start forming around the ice tray surfaces and then grow. So, therefore, homogeneous nucleation is nothing but a theoretical postulation which allows us to understand how the nucleation happens. So, our first discussion in the next lecture will be on homogeneous nucleation and to build a theory upon homogeneous nucleation, and then slowly we will move on to the heterogeneous nucleation because that is more complex. That is why it is better to start with the homogeneous nucleation. To give you an idea, in a homogeneous nucleation, okay, that is what is shown on the left side. This is a big cube, suppose, or a system in which nucleation can happen anywhere it can happen. There is no preferential things. Okay, anywhere it can happen. That is what I have written it blank and I am now filling up with the nucleus. But on the other hand, heterogeneous nucleation will be happening on, you see, on the surfaces or the boundaries or the corners, wherever. So, this is hetero, that is what we would say, and this is homogeneous. So, finally, it is very easy that because there is no preferential sites for the nucleation in the homogeneous nucleation, very easy to deal with it. It is much easy. Only important factor is that we create an interface between the solid and liquid. So, therefore, we must take care of the interfacial energy. Fine. So, I have just introduced the subject, and nucleation is very generic in all the system, whether solid or liquid solid phase transformations or even vapor to solid phase transformation, it is always present. But theory of nucleation will be generic, it will not change whether we are having a different type of phase transformation. So, whatever you are going to learn in the next few lectures is very generic, which you have probably learned in some other subjects. It will be simply recapitulation of the whatever you have learned in your other courses in material science engineering, but still for the sake of understanding or completeness of the understanding of the phase transformation, this is important, because we will be doing calculations using these equations in your assignments or in your exams, and so therefore, these equations or the theories of the nucleation must be known.